Okay, good morning once again, and we will come back to, and we have proving, our last class we have proved phi star of psi, the how the convolution makes the convolution smoother operator smoothing. If one of them is smooth, then the convolution product is smooth. Yeah, there is a one small correction which I want to make it here, and what is that error? Yeah. So, we apply basically what you do is that mean value theorem here. Yeah. Once you apply mean value theorem, one h will be coming out and that h will get cancelled here. So, there is no h here basically. So, there is no h here. So, okay. And because of that there is no h here also. So, there is no h here. Okay. So, there is no h here because that, you know, yeah, that you would have noticed it already if you are comfortable with that. So, there is no h, and then the remaining part is definitely is fine with that one. Okay. So, now let us go to the next theorem, some results from the next theorem. So, assume, so we will start with some, it is basically a remark and eventually leading to some theorem, nice approximations. Okay. Suppose f is, assume f is continuous with compact support. Okay. Okay. Recall modifiers, that is our thing, recall modifiers. Rho epsilon, you know that the rho epsilon is C infinity with compact support. So, it is this also has compact support. Okay. So, this implies of phi star phi epsilon, if I define convolution with f, okay, this will be C infinity and it will have compact support. Okay. So, it is a C infinity and has a compact support, and you can mentioned earlier the support of phi epsilon will contained in support of rho epsilon plus support of f. Okay. So, you will have that one, and support of rho epsilon is contained in B epsilon 0, a ball of radius epsilon. So, that is contained in B epsilon. You can take a bigger ball, and this is contained in B10, oh sorry, let me take, follow the standard notation B10. This is the ball of radius epsilon. Okay. So, we are assuming epsilon small, 0 less than epsilon, which is a parameter always going to 0. Okay, parameter going to 0, so small one. So, this is B10 a fixed plus support of f, and I call it k. This is independent of epsilon. That is how you have to call it, independent of epsilon. Okay. And let me call it. So, let us see phi epsilon minus phi epsilon of x minus f of x, you modulus. What is this? This imply this is in f of x minus y modulus x minus y rho epsilon of y dy minus f of x. Recall integral of rho epsilon is equal to 1. So, I can put this rho epsilon of y, this is x, rho epsilon of y d of y, this is an Rn, is also in Rn. So, that makes it less than or equal to integral of modulus of, I can take f of x inside, does not matter, f of x minus y minus f of x into modulus of course rho epsilon you do not need modulus because it is a non-negative, it is all non-negative functions. So, it does not matter. So, you have this one. So, now f is continuous, right, f is continuous on k and hence it is uniformly continuous on R. So, we can say, so f is uniformly continuous in k. Okay. So, that means that implies, so I choose the parameter slightly, epsilon is already fixed. So, I will given that epsilon, given theta, so I will do correctly, given theta positive, there exists epsilon positive. So, there is a interchange I am doing, it does not matter, such that modulus of f of x minus y minus f of x less than or equal to theta for all mod y less than, x is fixed. Okay. So, mod y less than or equal to epsilon. This is about the uniform continuity. So, with that uniform continuity, this is less than or equal to theta, because you can take this this is less than or equal to theta, you can take it that out and integral of the whole thing. So, this is actually less than or equal to theta here, this is less than or equal to theta. Okay. So, that implies phi epsilon of x converges to f of x. So, you see, which you would have seen it in some other way. So, I will write it in this form of a theorem. So, this gives you the following theorem. Thus, we have, okay, thus we have the following theorem. So, let me state it, we will use that one. The other theorem we will only give the steps. Okay. Let f be continuous with the compact support. Sometimes you may not need the precise form of rho epsilon. So, it is in, let me write it in the general form, compact support, then there exists C infinity functions, you see C infinity functions with the compact support, functions phi epsilon and a compact set k, that is what we have proved, and a compact set k says with support of phi epsilon contained in k, that fixed compact set contained in k, and phi epsilon support of phi epsilon contained in k and also support of f contained in k, both, you get both, right, that is how we proved it, both contained in k, you see, and phi epsilon converges to f uniformly in k, you see. So, you can, a very continuous function can be approximated uniformly by such functions, you can do that. So, that is a more general theorem, I will you would have already seen it in preliminaries, but now you have seen the whole concept of convolution in detail. So, whichever you could not fill it up there, now is used it, but you will get that one. Okay. Let 1 less than or equal to p less than infinity, then d of Rn is dense in LP. Okay, LP of R. So, that gives you, you have already done that. but for the sake of completeness some sort of little bit of repetition you can do that one. So, but I am not going to, this theorems are proved in 3 steps. So, I will not do that. The first 2 steps you would have seen it already. Okay. The step 1 is approximating a, so you start with the f is in a LP. So, you what do you do is that, so let me before taking the steps the proof, of course some sketch. The one, this theorem is the in the 3rd step you use it basically prove a stage. So, let f be in LP, okay. LP of Rn. Note that you do not get density in L infinity, be careful that LP. So, 1 less than equal to P less than infinity. So, you have 2 steps easily. Step 1, if f is positive, which I am not going to do it, there exists symbol phi, symbol function phi m with 0 less than or equal to phi m and less than or equal to f less than or equal to f, that is and phi m increasing to f, okay, that you can prove it. And then you can this will also go for general f, this is the measure theory thing which you have studied. So, I am just quickly recalling if not done in our preliminaries. You can write f is equal to f plus minus f minus. So, there exists phi m psi m as above for f plus and f m such that phi m minus psi. These are all simple functions. Yes. So, step 2 is your Lusin's theorem. Step 2 is your Lusin's theorem. So, precise statements you will see, as I said, these are all quick recalling Lusin's theorem. And so, if f is a simple function, so you have for proved f LP you can already approximate and you can do many things. So, recall all that the approximations. So, if f is simple or phi is simple, is a simple function, okay, then essentially you can say that there exists a continuous function with a compact support, continuous function with compact support, and phi can be approximated, except on a set of I think small measure, except on a set of small measure. Okay. So, there are a lot of things to this. You have to probably look into the Lebesgue theory when you study Lebesgue measure theory. Okay. So, I will not give the detail. So, what in step 3 is it's enough to prove. So, step 3 tells that it is enough to assume, f is continuous with compact support. This is continuous with compact support, okay, because other LP functions can be approximated. So, you have done it in 2 steps. LP functions approximate simple functions and simple functions with the continuous functions with the compact support. Now, at this stage recall the previous theorem. Okay. What is the previous theorem tell you? There exists phi epsilon. I am repeating it so that C infinity with the support of phi epsilon, support of f, contained in K with a fixed compact set K, and phi epsilon converges to F uniformly on K. So, with this you can prove that implies you can compute now the LP norm. Your LP phi epsilon or phi m a sequence, it is enough to take even a sequence. Phi epsilon is also fine. We are not comfortable with the phi m. Phi m. Okay. So, phi m minus f power p is actually this integral over K, okay, because the supports are there, f minus phi m power p, and now this has a supremum. So, this is less than or equal to supremum of f minus phi m power p into measure of K, which is a finite quantity. So, you see, and this goes to 0, that is the uniform convergence. So, you have the uniform convergence and you have that proof. Okay. So, that is where about the convolution of functions. Now, we will move on to distributions. Okay. So, this we will do it in 2 steps. First, we will do the convolution of a function with a distribution, and then finally, a convolution of 2 functions. So, I mean I do not know, I will prove it everything, and then we will see. So, the convolution of a function with a distribution. You already seen that one of them should have compact support. So, we will see that convolution. So, okay. So, how do we proceed? We follow our same principle. If you want to define the convolution, anything, if you want to get a formula, you look for the distributions generated from functions. Once you have a distribution generated from functions, and then look at the whether it will motivate you any formula. So, let us try to write down one of the usual convolution formula in terms of the distribution generated by one of them, that is all. So, you take f and g, take f and g. So, I am going to rewrite that. This is a kind of a motivation. Take f and g, then look at your f star g at x. Okay. I will put the conditions so. This is equal to integral of f of y g of x minus y d1. So, this is something tau f acting at this function. So, I put a notation now. So, I need some 2 notations. I want to write it. So, I will define. So, I will define an inversion operation. We call it g church of y is equal to g minus y. Okay. And a translation tau x of g at y is equal to g of y minus x. Careful when you use different books, whether they use a t y minus x or y plus or whatever it is, which way you are trying, which is the notation correctly used, translation to the other side or left side or right side, whatever it is. So, I am using this notation. So, to be careful, yeah, do not change it all that. Yes. So, with this I can write this is equal to f of y, okay, and this is x minus y here, y minus x here. So, an inversion is taking place and then a translation is taking place. So, this is nothing but g church of y minus x, and then that is a translation. So, that is nothing but then you have translation of the function of g chess at y. So, you see. So, this is the format you want it. So, this is the action. So, if I see that f the Tf is the distribution generated by f, this is nothing but your df acting at tau x of g chess. So, the question is that this is meaningful. Of course, this is meaningful, this is well defined, if g is in d of Rn, you see, may be well defined for other things. If T is a special distributions with compact support, it may be well defined, but at present we want to generalize for general distributions. So, you need G to be d of Rn, the translation, inversion, everything is in d of Rn. So, smoothness or the compact support will not change it. So, this is how you motivate. So, now this definition is suitable for any distribution. With that you give a definition. Let T be any distribution, okay, and phi is a function in d of Rn, then keep, this is a very important thing, you are defining the convolution keep this in mind, all the T star of phi is defined as a function, that is very important. So, even though T is a distribution, if phi is a function, T star phi is a function defined as a function given by T star of phi acting at x is equal to T acting at tau x of phi chess. You see. Okay. So, this is well defined because tau phi is in d of Rn, tau x of phi chess is also in d of Rn, and you can see that T star phi is a well defined function here. Okay. Later you will see the other properties of that one. So, I will tell one important property and then probably I will stop because the last lecture was bit long. So, we do not want too much things to do with you. So, some important remarks you give. This is, you have to keep that, this is a very important remarks. So, what do you have? So, recall. So, we have T star of phi at x is equal to T of tau x of phi chess. So, put x equal to 0, you see, put x equal to 0, that will give you T star of phi at 0, no translations. So, this is phi chess T at. Equivalently, this is also there, equivalently T at phi, because phi you can apply for T star of phi at 0, T of features, and T star of features of 0 will be T of features. So, that means that if phi 2 times inversion, that will be T of phi. So, you will get T of phi is equal to T star of features at 0. That means your distribution can be completely recovered by its in convolutions, that is a convolution product. So, that means knowing a distribution is equivalent to knowing all its convolutions at the surface. So, the message is that T can be completely recovered. So, whether T of phi is given or T star phi is given. So, if you are given T star of phi for all phi, your T is recovered. A distribution can be completely recovered, its convolution product. T can be completely recovered. These are all important things to understand. You will see a later theorem at the end of it, completely recovered from its convolution products, from its convolution product. An important message, you should keep it in mind. Okay. In particular, T star of phi equal to 0 implies T identically 0. That means T is a 0 distribution. Okay. And one more remark, this is one important thing and remark. Now again recall the definition, okay. T star of phi at x is equal to T acting at tau x of features. If T has compact support, that means T is extended to E of R and T acts on all functions on phi in C infinity of Rn. You do not need the compact support. That means support, then T of tau x of features is given for all phi in C infinity E of Rn, that is nothing but C infinity. So you see, so it is enough. Thus T star phi is defined either for T is a general distribution as given the definition, but phi has to be in D of Rn. Okay. If this is the case, T star phi is defined same definition, or for T is a distribution with compact support, that means it is in E prime of Rn, but then it is enough to have C infinity of Rn. You do not have it. So the definitions of all our results later, you will see that. So you see the distributions, arbitrary distributions are defined, the convolution of an arbitrary distribution with a CC infinity function is defined as a function, and later you will soon going to see the smoothness. Okay. These are all going to be C infinity. So you are going to approve, or T is a distribution with a compact support and phi. So it is just like a function, two functions f and g continuous with one of them compact support, you can define. Similar T and phi with one of them has compact support, then you can define your T star of phi. So we will see some property, we may or may not prove it, maybe if time permits we will prove it later, but we begin with the important properties in the next class. Okay. And that is it. So thank you very much. We will continue in the next class. So we may finish the whole thing in another couple of lectures. Thank you.